他会报告boundedness of Lustig A function for cost group of finite rank。欢迎。
好，首先非常感谢邀请，我很荣幸能在 ICCM 这个会议上，做这么一个报告。就是由于我的内容就是说，还有一些相对技术化的东西，所以我用中文讲起来比较方便。就是好，我主要介绍一下我们最近对 Lustig A 函数有界性猜想的一些进展吧。这个 A 函数是 Lustig在1985年提出来的，就是它被证明是是研究包腔基环还有一些表示论问题的一个非常重要的工具。其中有个长期悬而未决的问题，就是这个Lustig定义的 A 函数是不是有界的？我们最近就对这个问题给出了一个肯定的回答。这个工作是跟湖南大学的胡鸿生老师合作的。好，这个问题是对一个就是带权的 Cox 群来提的，就是说带权的 Cox 群就是这么一个三元组，其中那前面两个 WS 就是一个 Cox 的 system， 也就是说 W 是由这些就是由单反射集 S 生成，然后满足这些关系式，然后其中这个 L 就是这个全函数，就它是 W 到这个自然数集的一个映射，然后满足下面这个条件，其中这个小 l 就是我们常见的就是通常的那个长度函数，由此可见就是长度函数是一个特殊的全函数，如果全函数正好等于长度函数的话，我们称为我们就称为等参的。好。那么关于这个 WSL 这个系统，我们就有个 Hecke 代数，它是就是 ZVV 负1，就是那个罗朗多项式整系数罗朗多项式环上的一个代数，然后它的基是就是基是 TW， 它就是由这个W 中的元素参数化的一组基，然后就是这个是 Hecke 代数的那个基本的乘法公式。好。有了这组基之后，那我们就可以定义这个结构常数。我们就是设关于这组基 TW 的那个结构常数是 fxyz 啊，它们当然是关于 V 的一个罗朗多项式啊。那么我们可以讨论它的次数，对吧？对每个 fxyz 讨论它的次数。好，那么什么叫有界？就是对这个 WSL。来说，什么叫有界？这个定义很简单，就是简单的说，就是这个刚刚那些结构常数 fxyz 的次数，就是关于 xyz 是一致有界的，就是说它永远小于等于一个常数 n 啊，然后这个 n 就称为这个 WSL 的一个上界。好，下面就是说这是一个。那个 long-standing conjecture， 就是习老师首先是1994年，就是对这个等参的情形提出这有界性猜想，然后 Lustig 是对一般的带权Cox群，提出这个猜想，这个猜想是这样说的：如果这个单反射的个数有界的话，那我们就是上面定义的这个数就是 WSL 的一个上界，这个数就是指的是这个。就是全函数在这个有限抛物子群的最长元上的取值的那个最大值。好，一旦能找到一个上界的话，那么我们就是一个推论，就是Lustig A 函数是有界的。当然这是一个很强的猜想，就是说，至今为止我们还没有 idea 去证明这么精确的一个界。但是我们证明了，就是说，这个存在一个上界，就是说证明了有界，就是说在许多情形下，甚至在就是说在绝大多数情形，就是它这个已经足够重要了。就是说，你只要证明这个上界存在性， 同样的就是可以推出的 Lustig A 函数是有界的。一旦是有界的话，就是它就有很多好事情会发生。这个就是不一定要一个非常 explicit 的界，就是只要这个上界存在比如说那个卢斯蒂格在03年提出了对这个带权的 cos 群提出了这个著名的15个猜想。好，卢斯蒂格并且证明了就是等参的情形，就是你卡斯当卢斯蒂格多项式的正性以及这个我刚刚说的有界性，然后可以推出这个就它15个猜想等参。当然不等参的时候，这个还不等参的时候就有许多困难，因为这个 KL 多项式那个正性是不对的。当然这个就变成 open 的东西。但是等参的时候，一旦我们回答了这个有界性的话，那么这15个猜想就全对了。好，那么第一个就是被这个 Jody Williamson 还有 Ben Ellis 那个证明了。这是卡斯当卢斯蒂格理论里面一个里程碑式的结果。好，那个有界性就是那个至今为止是一个悬而未决的问题，我们想办法回答它。好，当然有界性它还有很多其他推论，比如说等参的情形可以推出这个最低双边包腔是存在的。然后比如说还有这个那个卢斯蒂格那个渐进环是那个 well defined 等等，它应该还有其他的我不知道的这个。好，那么就是说，当然这个问题部分情况是已经被证明的。就是说我在这儿列举一下，就是第一个当然是最简单的，就是有限的 W 是有限 cos 群的话，这个东西是显然的，那有界性是显然的。然后第一个不显然的情形是仿射性，它是一个无限 cos 的群。这个是卢斯蒂格1985年证明的，就是他证明了仿射情形那个 A 函数，它是被这个相应的仿射外耳群，我们有一个相应的那个有限外耳群，就是它被有限外耳群的那个最长远的长度给控制。这个卢斯蒂格也是在就是说那个这篇文章里面是首次提出了 A 函数。然后就是相继的有一些 partial result， 就是这个那个 Belolipetitsky 就是这个04年就是证明了这个直角 cos 群的情形，这个猜想是对的。什么叫直角？就是说你这个就换句话说，就是你 cos 的图里面要么不连，连起来就是无穷。然后习老师就是那新南华那个老师就是证明了这个那个 W 就是 W 的 cos 图是完全图的情形。也就是说，任何两个单反射乘积的阶是大于2的。然后就是不久以后，就是马上被石老师和他的学生杨高那个推广到了那个一般的带权 cos 群。然后就是那个然后就周培培那个证明了这个等参的那个单反射个数为3，就是我们简称质3嘛，就是那个质3的情形。然后就是不久以后就被这个就被高建伟那个推广到了那个带权的 cos 群。然后呢，19年就是石老师和他的学生就是证明了这个任何两个单反射乘积这个不是3的情形。然后他们同时也验证了质4里面的一部分情形。就是说以上结果都是已经被证明的，而且就是他们也达到了原来所猜的那个结果。好，下面就是我们的主要结果，就是如果是有限制的话，就是说这个东西就是 bounded 的。就是当然我们就是当然我们就是像我一开始提的，只是有界不是就是那个并没有证明就是原来猜的这么精确的那个界。好， 那么我们先把这个，那我们先讲一下就是那个overview 啊，就是粗略的，就是那个粗略的讲一下我们这个证明的主要步骤，就是一共分为3步，就是第一步第一步是很自然的，就是我们要考虑结构常数这个次数是否有界，是吧？那我们把 Tx 乘 Ty 展开来啊，就是展开成就是说展开成这么一个形式。具体怎么展，我后面就会介绍的。然后就是说这些，就是这些 TZI 的那个线性组合，就是那个线性组合，前面的 KCI 当然是系数啊。就是说这个求和，就是这个求和里面的这个那个上面的这个求和项，它是被这个1到 Ly，就是这么里面一个子序列给某些子序列给参数化的，并且就是说这些 KCI 的KCI 的次数是不超过这个数的。好，那么这个东西怎么用呢？就是说要证明我一开始说的那有界性的话，只要证明这里面所出现的 KCI，关于 x、y 是一致有界的啊。注意，就是说注意这个 KCI 是和 x、y 有关的，就是说 xi 就是 x 和 y 要变的。那不然的话，你 x、y 固定，那肯定是有界的，对吧？次数。因为你展开了就有限多项，这个 x、y 要变的那个情况下，就关于这 x、y 要一致有界，那么已经有这个不等式了，而且你这个东西是一个常数，是吧？那只要证明这里面所出现的那个子序列这个 I 的这个长度是一致有界的就可以了。好，第一步是比较自然，然后关键的是后面2步，就是因为这是一个那个就算是这样。就是你考虑 KCI 的这个次数，还是一个非常就是说非常复杂、非常组合的问题，就是因为你任意寇克斯群里面的那个元素的那个表达式啊，那个最简表达式，那这个是非常复杂的，就是所以你用纯代数、纯组合的去考虑，就是考虑它，就是估计它的上界的话，这个目前看来很困难。为了解决这个问题，我们引入了所谓的 intersecting set， 就是相交集的概念。就是说，第二步我们证明了，就是那个每一个这里面每一个求和项，就是那个求和项是被这个子序列 I 指标化的，对吧？也就是说，那这里面每出现一个求和项，那个对应那个子序列，就是关于这个子序列，我们可以找到一个。那个大小和 I 的长度一样的这个相交集就是每一项都产生了一个那个大小为长度，就卡迪内利为 I 的长度的一个相交集这是一个就是说这是一个几何上的概念，就是，然后就是最后一步，当然就剩下的就是证明这个相交集就是说所谓的相交集的那个大小是有界的。然后，当然完成这3步的话，我们就证明了一开始那个有界性猜想。好，那么我们把这个 overview 给展开来，稍微展开的细一点。那么展开来，我们需要一些 well-known 的这个概念。第一个是 Cox 群的几何表示当然它是一个实线性空间，然后它是由这个它是 spanned by 这些那个单根然后你 V 上就是装配的这么一个对称的那个双线性形当然这个角度可以五花八门，这个远非欧式几何，就是远非欧式空间这个内积。然后对每一个单反射，我们定义那个单反射的作用，就是关于 B 的这么一个反射这个就是自然的定义了这个 W 的一个表示，那我们称为几何表示，或者说自然表示。这个第二个是那个 Tits 控，那个 Tits 锥，就是我们是引用 Humphreys 书里面那个定义，就是说我们在 V 星上面定义，就是 V 的那个线性函数，我们把这个 C 就是这个 fundamental chamber， 就是定义为这个在所有的单根上取值为正的 那个线性函数的全体，然后我们 C 取 B 包以后，通过 W 作用一下，然后把这些外尔房的 B 包给并起来，这个就是称为这个 T-score。其实我们经常把外尔房跟这个 ARCO 可以等同起来看，因为外尔房是个 simple ratio cone， 它是一个锥的结构，然后你把它截一下，然后用单位球面把它截一下，就变成一个 ARCO， 就是我们也可以把它说成一个那个 ARCO， 是好，这个 T-score 的话，其实是就是其实被证明它是一个，就是说它是个 convex cone 凸锥，然后它的内点积，这个内点就是因为 V 星号有个自然的欧式拓扑嘛，这个里面就是说里面这个内点积是这个 open 和 convex 的，开的和凸的。就是说，当前紧到 W 是有限，就是有限外尔群的，有限 cos 群的时候，这个 U 就是和这个，这个 U 就是整个空间啊。这有限的时候，其实这个有限的时候，这个其实这个 B 是非退化的，有限的时候甚至是对，甚至是那个正定的。所以我们 V 和 V スター可以通过这个双线性型可以 identify 的，就是外尔群的时候就不区分 V 和 V スター。但是我们一般情况是这样定义的，就是一般情况的话，无限的话，它这个不是正定的，然后 U 也不能等于整个空间，就是这个时候 U 就是这个那个半空间 B 的那个，就是说那个 B 的半空间里面的一个锥，可以证明仿射情形，其实就是说那个其实就是这个开半空间再并上一个，就是说那个并上原点。还有比方说典型的一类那个双曲 cos 群，那你这个 T 次锥是落在这个光锥的 B 包里面的，因为双曲 cos 群有个敏科夫斯基内积，然后它的小于0部分可以定一个就是定一个光锥嘛，然后是在光锥的 B 包里面的那个好，下面一些记号是我们就是那个所熟悉的根系。就是说定义方式跟外尔群是完全一样的，我就不详细读了。就是根系正根系，然后就是对每个正根我们定一个超平面 H 阿尔法，然后超平面的这个集合我们记为化写的 P， 反射那个超平面集合，然后对每个反射超平面我们有这么一个反射，这个也是我们很熟的。然后我们常用的记号就是说，对每一个超平面 H 的话，这个它对应个正根阿尔法 H， 然后还有个反射，我们记作 sigma H。好，第一个重要概念 intersecting set 那个相交集，这个我们就是这个我们 overview 里面提到过的。好，对 V 星号的，就是说 V 星的两个子集的话，我们记这个。那个点交，那个 dot cap 指的是那个 A 和 B 在这个 T-score 内部的内点集里面的交。好，那么什么叫相交集呢？就是说它就是一个超平面的 family，一组超平面 Q， 我们称为相交集，相交的，那当前仅当这个 Q 里面的超平面就是两交在这个 U 的内部 U circle 里面，我就简称相交吧。后面我们就简称 H1 和 H2 相交，我们默认就是考虑在 U 的就是 U circle 的交。因为普通的相交在这里是没有意义的，因为 H1 和 H2 超平面都是子空间，你肯定是相交的，交在0肯定是对的，是吧？这个你讨论普通的相交在这里是没有意义的。我们就是关键是要考虑，就是在 T-score 内点处的那个是不是相交？那我们规定空集是相交的，那个并且我少写了，就是空集和任何超平面它是 就是它也是相交的，就是这个是对这个规定也是符合数理逻辑的，对吧？好，那么我们怎么展开呢？这个展开是很自然的，就是你把其中一个，比如说 y， 你 y 写成一个固定的最简表达式，你写哪个无所谓，写 x 也可以，这个难度是一样的。好，那么我们不断的就是乘以 tx 乘 ty 的话，就不断的乘 ts1 ts2，乘以后再就是完全展开不合并，就是不难证明它展开以后是这个样子，是这么一个组合。然后其中每一项 ci 是这样的，那个 ci 是ci 是在这个 x 乘 y 的基础上，挖掉了其中某些项，这个 hat 就是就是说把这个项给挖掉。当然不是随便挖的，就是要满足这么多个 pi 就是 i 的长度，就是这里面所出现的那个 i 的长度。这个 pi 个的布鲁海的序关系，这我就不细读了。当然就挖掉的位置就是对应的这么1到 k 就是 ly 这么一个子序列，是吧？每一项都是满足这个条件的，满足这么多布鲁海的序关系条件的那个子序列。好，那么我们这个就是 overview 里面的第2步，这个就是你这么就说就是刚刚说了每一个值和就是每一个求和项就是那个所对应的子序列要满足，就是所对应的子序列 i 要满足这么多个布鲁海的关系式。那我们第一个结论就是说，我们可以从这么多个布鲁海的关系式出发，构造一个大小正好是 i 的长度的相交集。也就是说，每一个求和项对应了每一个对应就是那个对应子序列 i 了，每个求和项对应那个子序列 i， 也就是说，每个求和项就是导出了，根据每个求和项就是可以找到，就是找到这样一个那个相交集，就是这个大小等于 i 的长度的。好，那么我们直接构造这个 Q， 目前看来是我们没找到一个直接的方法，就是说一下子把这个 Q 给造出来，所以我们就是递归的构造这个 Q。Q 的那 cardinality 太大，那我们我们取而代之的是找那个就是不断的找 cardinality 为 n 的相交集，对每个 n 到就是说那个 n 到 pi。Q1、Q2、Q3 一直到 QPi， 然后就是使得每个 cardinality 为 n 的这个相交集满足这么5个，就是那5个和 n 有关的性质，然后我们最后令这个Q 就是最后一个 Qn 这个 QPi， 相当于我们把这个命题给加强了5个性质，然后其实我们就是对5个性质。就关于这个5个性质对 n 做归纳，这个5重的，就是我们就是递归的找，从那个，就说我们假设 Qn 减1已经找到了 ，n 减1的 cardinality 的大小已经找到了，再就递归的构造，然后再找 Qn。就是前面2个蓝色标记的性质是我们真正想要的，就是这个 C 就是 cardinality 那个条件Qn 的大小是 n， 然后。那 in 这个就是代表就是 Qn 是这个相交集，这个首字母就是为了方便记忆而用的，剩下3个是技术性的东西，那个是剩下3个性质，实际上是辅助性质、技术性的东西，我就不详细展开了，就是保证我们的归纳可以顺利的一步一步进行上去的这个那个辅助性质，就前面2个是我们真正想要的。就是说那个证明更强的，相当于证明更强的东西。好，那我们构造这个递归的构造 Qn 的出发点就是一些特殊的超平面。这里我们直接看这张图，就是画的，就是那个这儿画的这个 H1 到 HPi 吧。是什么东西呢？ 就是我们回忆一下，我们一开始固定了 y 的一个最简表达式 S1乘到 SK， 然后这个最简我们知道 cos 型里面最简表达式在 Arco picture 里面就是对应了这个从 xc 到 xyc 的一个最短反射路径，然后每反射一次都从 Arco 穿到另一个 Arco， 就是穿过一个超平面。其中有些特殊的超平面，就是这个 H1 到 HPI， 就是对应于刚刚我们删掉的这些项的 SI1 到 SIPI 的这个删掉这些项的那个超平面，就是。然后我们记这个对每个 n 的话，然后我们记 xnc 就是就是说在这个路径中贴在 hn 左边的那个，那我就形象的讲了啊，就是贴在 hn 左边的这个 Arco。那上面其实就不用看，就是说这个 sigma n 就是我们记 sigma n 就是关于这个 hn 的反射，然后就是那个，然后这个en 就是这些反射的复合啊，这个。那我们出发点就是这些，就在超平面 H1 到 HPI。好，这三个是技术性引力，我就不详细读了。其实就是概括的说，就是这个就是说这个技术性引力就是主要是在讲这个超平面 Hn 就跟这些 Arco xec、xnc 啊等等这些 Arco 之间的相对位置关系，就是说什么时候在同侧，什么时候在异侧等等，就是相对位置关系。好，那么我们看简单的例子，这个 n 小的时候，这 Qn 怎么造的 ？n 等于1的时候确表啊，这个 n 等于2的时候，就是上面那个技术性引力里表明了，就是说表明了3点，就是那个第一，就是说 x1 和 e1 这两个 Arco 是在 H1 的这个同侧，然后第二就是说存在 H2 上的一个点在 H1 的另一侧，然后第三就是。H2 是分割这两个 x1c 到 e1c 这个 Arco 的，你结合这3条，很容易证明 H1 和 H2 是我刚刚说的意义下相交的，太直观了，对吧？这个你如果要严格，你如果严格写的话，就0点定理吧，这个都很粗的啊。好，就是好，所以我们 n 等于2就是简单的 H1 H2。n 等于3，它不是非常的确表，就是它是一个 toy example 典型的例子，就是说你因为 n 等于3情况会复杂点，它会有2个 case sub case， 我们在 case 1里面，我们首先假设这个，就是说 x1 和1就是这两个东西在 H1 的同侧，同侧的话那就好了。那根据刚刚那个方法，同样的方法可以证明 H3 和 H1 相交，并且和对，因为它也在 H2 的同侧，也是根据刚刚那个技术性引力，那么就它也和 H2 相交，然后 H1 和 H2 是归纳假设，刚刚像在 Q2 已经造好了，相交啊，这个时候就取着这个，看上去还比较确认。而不幸的是什么呢？不幸的是这个 H1 有可能会分割这个 x1 和1、2的。在这种情形的话，这个 H1 和 H3 可能在 U circle 里面是不交的，甚至在仿射 L 里面，仿射 L 你对应的就是欧式空间里面那个平行线，仿射 L 情形的话，也有可能是不交的。所以我们要做适当的调整，我们才可以得到想要的这个 Q3。怎么调整呢？我们考虑这个把 H1 反射成它，我们关于 H2 反射成这个东西。一旦反射以后，不难证明这个 x1 和1、2，虽然说在它的一侧，虽然说在 H1 的一侧，但是在反射以后的这个同侧了。一旦在反射以后的同侧的话，又回到了。如果我们考虑这3条红的话，就是又回到了上面那个情形了，所以也就同理，这3条红的 hyperplane 那个 intersecting 的。好，所以就是情况没那么简单，就是它至少提示了我们，就是我们要递归的造的话，你必须要对 Qn-1做适当的调整，调整之后再添加最后那个 Hn。好，那么一般情况怎么调整？那我简单的那个 sketch 一下了。这个一般的情况的构造，这个 Q1 刚刚已经讲过了。然后假设我们 Qn-1已经造好了，然后我们想办法调整。好，那么怎么调整？就是先把它分成2部分，这个无交并，我确定其中一部分就行了。比方说我们确定 A， 就是根据刚刚那个东西的启发，就是我们要构造 A 的话，先从这个A0开始，就是它因为有可能这个 P 这里面的 P 会分割这2个 alcove 的，有刚刚的例子啊。那我们把这个集合拿出来，这个分割2个 alcove 的那个超平面拿出来。那我们从 A0 出发。Qn-1啊，这个我们从A0 出发。好，那个拿出这个 A0 以后，我们希望什么呢？就是 A0 中的超平面和剩下的不一定是什么，就是不一定是这里任取一个和这里任取一个都相交的，这完全不一定的。那我们根据刚刚的例子，自然希望就是说你反射之后 ，A0 之后，就是 A0 里面超平面反射之后和这里面的另一个超平面都交。但这个东西不一定，里面可能有，就是说剩下的超平面里面可能有一些跟 A0 中的所有超平面反射之后不全交，所以我们不全交的再取一部分，对吧？再取一部分那个出来，把这个看成新的 A0，然后剩下的是不是有刚刚说的这些好事情呢？也不一定啊，没有的啊，再拿一个出来，再拿个 A2 出来，然后我们一步一步，那么这递归那么找下去，然后这是一个有限集，找到一定程度，这个就变空集了，完了，然后这个就是不断的这个最后这个 L-1吧，然后把这个作为 A 吧，好，所以我们基于这个想法，就是把它那个就我们这 AI 是递归构造的，就是你假设前面一些已经那个造好了，然后你剩下的就是这个 AI+1就剩下的里面超平面里面那个与这个 sigma n_ai 这个里面的超平面不完全交的这个 P 的这个全体 sigma n_ai 就是说把 AI 里面所有的超平面关于这 Hn 都这么反射一下。好，那我们就是根据刚刚这个讲的并起来，那并到一定程度就没有了，其实后面都是空集的。然后我们那个 B 当然就补集了，然后就是我们 Qn 就是说我们就是反射一部分，就是说反射我刚刚找的一部分 A， 然后 B 这块不动，然后再添加 Hn。当然还有一个技术性的活，就是证明这个 Qn 是我们真正想要的，是不是满足这么就是这个5个性质？这里就是对 n 做归纳啊，然后这是我们最这个就是这个最技术性的东西。好，那我们第2个关键就是证明这个。好，刚刚我们就是因为每个求和项展开之后，每个求和项得到了这么一个和这个 Xi 和这 i 长度一般多的相交集，然后剩下的自然就是证明这个相交集的这个大小是有界的，啊，这是第2个关键啊。这当然我最初给出的证明是非常繁琐的，然后我的合作者胡鸿生就是给出了一个简化的证明，啊，想法是这样的，我们需要两个简单的引理，就是 这个几乎就是个已知的东西。这个就是第一个是说你这两个超平面，就是说相交的话，当且仅当这个相应的这个b值是在负1到1之间的。然后第二个是说，如果是有限制的话，就是你这个在负1到1当中的这个 b 值就只能是有限多个。比方说我们记得几何是 C1 到 Cm， 就是这种值，就是说就这样的阿尔法贝塔的 b 双线性只能取有限多个值。就是假如是在负1到1中间啊，那其他的那可能是无限，对吧？那我们只关心这负1到1当中的那个 b 值。好，那我们那个 summarize 一下，就是说我 Q 就是一开始那个相交集吧。那么相交集的话，那个推论就是说，那关于就是相交集里面这样的就是说这样的那个 b 值就是只能取有限多个值，就刚刚那个最多取这个 C1 到 Cm 那么有限多个值。就是说这个个数只跟这个 Cox 群的那个基础数据有关，就是这些那个 MST， 跟其他的完全没关系啊，只跟这个 Cox 群本身有关的。好，我们把 C1 到 Cm 想象成 m 种颜色，然后我们就可以构造一个染成 m 种颜色的一个完全图。这个顶点就是跟这个相交集里面超平面一对应，你一个超平面对应一个顶点，然后呢就是你这个每条边啊，就两个超平面相当，每条边染色就是按照它就是按照这个 b 的取值染色的。根据这个规则，就是我们产生了一张这个 M 色的这个就是最多为 M 色的完全图。染 M 种颜色的完全图，那我们就是可以联想到经典的拉姆塞定理了。你如果这完全图的顶点足够大的话，足够多的话，你肯定会有染某种颜色的完全子图会足够大。拉姆塞定理这么就粗略的讲啊。精确的讲，你要用拉姆塞 number 这个，就是粗略讲反而好理解啊，这就我刚刚说的，就是它肯定有个子图，纯色子图会完全大的。换句话说，我们要证明这个 Q 的大小有界的，就是这个图的那个顶点个数有界的，那我只需要证明染纯色的这个完全子图的这个大小是有界的就行了。就归结成染纯色的这个情况，那么再翻译回来，就是说我们只要证明这种相交集 Q 撇这种相交集，使得什么呢？它们就是说，使得这样的 b 值都是常数的，都完全相等的，这个就是那个这样的相交集 Q 撇的大小是有界的就可以了。好，那么只需要证这个 reduction 的话，剩下的就是线性代数的东西了。然后就是比方说我们设这个 b 值都是 a 吧，然后我们关于这个双线性性 b， 关于这个就是这些向量阿尔法 q 这些根都有它有一个格拉姆矩阵。这个是本科生的练习题，这就是这个矩阵的值。显然由这样的公式给出啊，这个好，那这样的话就是说你这个向量组的值就是那肯定是要大于这个格拉姆矩阵值，然后就是根据刚刚的超过它啊，然后就是这个值当然不超过 v 的为数的啊，这些都大一的东西，然后所以就是这样的 Q 撇就是。bounded by 这个东西，有上界的，但这个东西是个固定的数，是吧？那么就是说染纯色的这个相交集是这个有界的，相交集的大小是有界的。那么拉姆塞定理导出了这个，它因为是那个固定的最多 m 种颜色，那肯定整个是有界的。当然好，那么我们完成了，就是这样的话就完成了这个有界性，就是仅仅是只是这个有界性的证明啊。 就像我一开始所提到，就是我们这个界不是最优的，这个界比原来那原来猜那界看上去比较帅，就是但我们没挣到它。然后我们自然的就是想把我们这界和原来这界去做一些初步的比较啊，这个差多远？这我们现在因为没多少想法，只能做一些初步的，就是说初步的尝试。就是那即便是等参的情形，其实我们这个界也有可能比原来猜那个界要大啊。那么等参的情形就是说，我们把原来那个这个界就简记为 NW， 然后就在等参的情形，我们其实就是证明了这个东西，就是这个那 n 撇 W 这个数就是我们 W 的上界，这个 n 撇 W 就是这个相交集的这个大小的那个最大值啊。根据我们前面的证明，这就是个有限的。好，那么卢斯蒂克指出了，就是你这个 A 函数这个任何上界都会比这个要大。其实这个就是一旦被证明是上界的话，它这个就是下 a 的，正好是这个最大值。当然现在没有那么完美。没被证明，所以不知道啊。然后我们希望证明某些情况下反向的不等式也是对的，从而他们两个就对了，就是重合了。那么我们也只考虑了这个有限仿射质3但是时间关系，我就是简单的介绍一下最有趣的情形质3。我们直接看这张图。这个质3的话，我们知道质3的双曲 Cocos 的群，就是这个时候的超平面就对应庞卡莱 disk 当中的一些测地线，它画出来是弯的，其实，但我们方便我们就画成就是画成直线吧。比方说我们要证这个相交集的这个个数是不超过原来猜的界 NW 的，那就相等了。好，那么比方说我画5条吧，5条的那个相交集啊，然后我选取其中1条的横的，然后你其他的都交于1点，然后如图就是产生了那么4个角，对吧？那个4个角，但是我们看一下任意2个角什么关系呢？那任意2个角的话，比方说我们看西塔3和西塔，任意2个角都可以以这种方式产生一个双曲三角形。双曲三角形的内角和小于派，然后这个局部就放心的用欧式几何，什么对丁角相等啊，什么下面就是派减西塔3，这个放心用啊，局部跟欧式几何是一样的，它只是整体上不一样。然后所以这个三角形内角和小于派，就是马上就等价于说这个西塔3减西塔2是至少是这个，就是说大于这个阿尔法，但是这个在贴子控内部的，就是庞加莱圆盘内部，它这个角有一个，它肯定是这个最小可能值是它，这个。一般情况，那我们这个小 q 就是这个相交集的那个大小 cardinality。那么同样的，我们可以找到这么 q 减1个0到派中找到 q 减1个角，然后相邻的那个步长，相邻的这个步长是大于等于这个数的。它反正有个最小步长嘛，那肯定不能太多。那当然容易证明这个，就容易看出它肯定是不超过它，对吧？好，那这个时候就等于了。这个例子说明我们这个下界会比它有可能会比它大，我们这个界啊，这个 n 撇 W， 因为我们考虑这么 S2、S3、S4 这个抛物子，就是那个抛物子群，这个当然是 A3， 对吧？所以我们这个 NW 就是6，但是我们发现 S1 对应的超平面跟这个跟这里面的相应的6个超平面全部相交，全部在贴子控内部交， 那这个相交集的个数，相交集的大小，是吧？至少是7，是吧？这个就超过这个东西了。所以就是进一步，实际我们是要考虑，就是说怎么把这个界缩小。哎，当然最完美就是找到原来那个，证明原来的界，或者也可以反面的去想一下，原来那个界对不对，有没有反例？那个进一步的问题有很多。那我的报告就这些内容，谢谢。
Thank you for that. Any question? 什么问题吗？
我想问一下，那个你在构造这个相交集的时候，就是从一个SI 的子序列构造一个相交集，如果是你说就没有一个一次性把它构造出来的这样一个算法，一个描述？
没有发现，只是。
但如果在特殊情况，比如说就是有限外耳群的时候，
有限是显然的。
就是这些就不需要做调整是吧？
对，不用调整。有限因为这个 T 次控就是整个空间，你任意2个超平面，你肯定是在我这个意下相交的。你超平面的个数就是这个最长圆那个长度，有限是 trivial 的，就是。
那如果仿射的时候呢？
仿射的话，仿射可能卢斯这个85年的证明里面，应该也隐隐约约体现了这一点。就是它有仿射的时候，就是仿射的时候，就是在我这个意义下交不交，其实就等价于欧式空间当中两个超平面是平行还是相交。仿射的时候情况很简单，它因为仿射的时候超平面的法向量就这么，法向量的那个方向的个数啊，它就是和这个有限外它里面那个有限外耳群的长度，最长圆长度是一样多的。
OK。
那个。仿射还是比较新鲜。对，好。
Further questions? If no more questions, the thanks begin again. We will resume in 15 minutes. Okay, welcome back. We're very happy to have Zhiling Luo from Purdue University. He will tell us about non-abelian Fourier analysis in Lawrence program. Let's welcome.
Okay, so thank you for the invitation and for the introduction. Okay, so today I'm gonna share with you some of my recent work. Okay, on non-abelian Fourier analysis in Lawrence program. Okay, so I believe all the audience here know what is a classical Fourier transform. Okay, so if we have a Schwarz function on the real line, okay, which is rapidly decreasing, okay, then we can define its Fourier transform. Okay, it's just an integration against the exponential function. Okay, e to the 2 pi I c eta. Okay, then this transform has a lot of remarkable properties. Okay, so first, every time you have a Schwarz function, its Fourier transform is still a Schwarz function. Okay, and moreover, this transform preserves the L2 in the product or the L2 norm. Okay, of a Schwarz function. Okay, okay, and moreover, this transform is involutive. Okay, in the sense that if you apply the Fourier transform twice, okay, then you almost get the original function. Okay, and finally, we have the Poisson summation formula. Okay, if we sum over all the integer points, okay, then a priori, the function phi and its function have the so-called principle. Okay, if the function phi has support extremely sharp, okay, then the function phi to tend to the delta mass supported at 0. Okay, then its Fourier transform is gonna tend to the identity function on the real line. Okay, but it turns out that if you take the summation over all the integer points, you get the identity. Okay, okay. So this is called the Poisson summation formula. Okay. So Fourier analysis has broad applications in many subjects of mathematics. Okay, in analysis, geometry, physics, applied science, and the number theory. Okay. So our goal today is to focus on the non-abelian generalizations inside the Lawrence program. Okay. So let's recall some classical story about the Riemann zeta function. Okay. So I believe it was first discovered by Euler that for any real part of S bigger than 1, okay, he introduced a so-called zeta function. Okay, it's defined to be the following summation n from 1 to infinity. Okay, of 1 over n to the s. Okay, he showed that this series is absolutely convergent. Okay, and it has the following remarkable identity. Okay, it can be written as the product over all the prime number p. Okay, of 1 minus p to the minus s. Okay, parentheses 2 minus 1. Okay. Okay. So later, Riemann discovered that if we complete the zeta function by an additional factor, okay, pi to the minus s over 2, okay, times gamma s over 2, okay. So here, gamma s is defined to be the following integral, okay, 0 to infinity of e to the minus t, t to the s dt over t, okay. For any, this integral is absolutely convergent for real part of s bigger than 0, okay. And using integration by parts, you can show that the gamma function here has an analytical continuation. Okay, s times gamma s equals gamma s plus 1. Okay. Okay. Then for each individual term inside the product for Cs, okay, which is pi to the minus s over 2 times gamma s over 2 times n to the minus s. Okay. You can do some simple change of variable and write it as 0 to infinity of e to the minus pi n squared t, okay, times t to the s over 2 dt over t, okay. Okay. Then we take the summation over all the positive integers, okay, we get the following integral representation for the completed zeta function, which is Cs, okay. So for any real part of s bigger than 1, okay, C of s can be written as the integration of the so-called theta function, okay, summation n from 1 to infinity of e to the minus pi n squared t, okay, t to the s over 2 dt over t, okay. So in other words, we write the zeta function, also the Cassini function, as a Milling transform of the Jacobi theta function here, okay. 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 So here, the theta function, let's recall its definition, okay, it's defined to be the summation over all integers of e to the I pi n squared t, okay. Here, t lies inside the upper half plane, okay. So in conclusion, we can reformulate Cs here as the following identity, okay, is summation, is integration n from 0 to infinity of theta it minus 1 over 2, okay, t to the s over 2 dt over t, okay. So this integration is absolutely convergent for real part of s bigger than 1, okay. Then in Fourier analysis, we know that the Fourier transform of Gaussian function is just itself, okay. So for any t bigger than 0, okay, we let gtx to be e to the minus pi x squared t, okay. Then we take the Fourier transform in x variable, okay, you almost get the original Gaussian function, okay, but you switch t to 1 over t, okay, and you get a proportional constant, which is t to the minus 1 over 2, okay. And the Poisson summation formula gives you the following theta inversion formula, okay. Theta it is equal to t to the minus 1 over 2 of theta I over t, t bigger than 0, okay. Okay, so for those of you who are familiar with modular form, it just reminds you that theta function is a modular form of half integer weight, okay. Okay. So in conclusion, we can apply the Poisson summation formula to the integral presentation of Cs to get a non-trivial symmetry for the C function, okay. So a priori, the Cs here is integration from 0 to infinity. We break it to be integration from 1 to infinity and 0 to 1, okay. And then for the part from 0 to 1, okay, we do a Triennial variable changing t to t inverse and apply the Poisson summation, okay. Then we get the following, okay. So for the part of 0 to 1, okay, of theta it minus 1 over 2, t to the s over 2 dt over t, okay. You do some simple calculation, okay, then it's just minus 1 over s minus 1 over 1 minus s, okay, plus 1 to infinity of theta it minus 1 over 2 for emphasis t to the 1 minus s over 2 dt over t, okay. So in conclusion, we get the following expression, okay, because Cs here can be up to the fractions 1 over s plus 1 over 1 minus s. It's just an integration from 1 to infinity of theta it over 2, okay, of then times t of t to the s over 2 plus t to the 1 minus s over 2 dt over t, okay. And it turns out that right-hand side is entire is for any complex number, okay. So it's literally just absolutely convergent, okay. Therefore, in conclusion, we see that the Poisson summation formula for the theta series, okay, implies that the C function, or say the Riemann zeta function, okay, has a meromorphic continuation to the whole complex plane, okay, and with the following functional equation, okay, Cs is equal to C of 1 minus s, okay. Okay, so I believe most audience here have already seen this proof in maybe in undergraduate course, okay, but anyway, okay. Now let's see another example, okay, let's look at the so-called Ramanujan delta function, okay. For any z inside the upper half plane, okay, let q to the e to the 2 pi I z, okay, I forget the I here, okay. So the delta function is defined to be the following q series, okay, it's product q times n from 1 to infinity of 1 minus q to the nth power and then to 24th power, okay. Then you have, you can just expand this product, okay, and write it as summation n from 1 to infinity of some positive integer tau n here, okay, times e to the 2 pi I n z, okay. And you can show that this is actually a modular form of weight 12, okay. So for any a, b, c, d inside SL2z, okay, delta of az plus b over cc plus d is equal to cc plus d to the 12th power, okay, times delta z, okay. Okay, so this is also a modular form. Actually, it's a cusp form, but anyway, okay. Then we just do similar thing that we have done for the Riemann zeta function, okay. We integrate the delta function along the imaginary axis of the upper half plane, okay. Delta iy, okay, y to the s, dy over y, okay, integrate from 0 to infinity. Then by some simple calculation, you can show that it is equal to the following Dirichlet series, okay. It's integration n from 1 to infinity of tau n over s, okay. And it turns out that you also have a Euler product, okay. It's product over all the prime number p of 1 minus tau p, p to the minus s, plus p to the 11 minus 2s Francis, okay, 1 over, anyway, okay. Okay, and the well-known Ramanujan conjecture, which is now a theorem thanks to Deligne, okay, speculates that for any prime number p, okay, the absolute value of tau p, okay, should be lower than or equal to 2 times p to the 11 over 2, okay. So the proof of Deligne uses algebraic geometry, okay. But the natural question is that can we find a more analytical proof for this conjecture. Okay. So in the following, let's briefly recall the so-called Laurent's functoriality. Okay. So let G over a number field K, okay, to be a reductive group. Okay. If you like, you can just take G to be GL2, okay, over Q. And let's take rho to be a representation of the L group of G, okay. So if you take G to be GL2, then its dual group is just GL2C, okay. And you can take rho to be the symmetric nth power, for instance, okay. And we fix a pi cuspidal automorphic representation of G, okay. So roughly speaking, in previous slides, we have seen that Ramanujan delta function is a modular form, okay. So every time you have some modular form, you can attach to it the automorphic representation, okay. Anyway, okay. So Laurent's introduced a so-called Laurent's automorphic L function, okay. So it's just product over all the local place, okay, of some local L factors, okay. So at the unramified places, you can use the so-called Satake isomorphism, okay, to define the local L factors, okay. At the ramified place, you may need to rely on the local Laurent's correspondence, okay. But anyway, Laurent himself shows that these L functions are absolutely convergent for real part of S sufficiently large, okay. Okay, in case you have any question, you can feel free to stop me, okay. Then from triviality conjecture of Laurent speculates that these more general automorphic L functions, okay, just like zeta function, should have a meromorphic continuation to the whole complex plane, okay, with a function equation, okay. So if we substitute S by 1 minus S, okay, and replace pi by pi check, okay, which is conjugredient, okay, then L of 1 minus S pi check rho, okay, should just be equal to L S pi rho, okay, up to a non-zero entire function, which we write as epsilon S pi rho, okay. Okay, so in other words, these more general automorphic L functions should just behave like the Riemann zeta function, okay. Okay. Okay, so let us make the following observation, okay. So if we take G to be GL2 and then rho to be the symmetric nth power, okay, then if you can show that this general automorphic L functions, L S pi rho, okay, is absolutely convergent for real part of S bigger than 1, okay, for any n, okay, then it implies the Ramanujan conjecture, okay. Okay, and this, the observation of Laurent, okay, is known for those pi coming from holomorphic modular forms, okay. However, it's still open in general, okay. For instance, it's still open for mass waveforms, for instance, okay. Okay. And for GL2, the best record so far is just n equals 4, okay, which is due to Kim and Sanak over Q, okay, and Blumer and Brimley over general number fields, okay. Okay, and it is also connected with the so-called Selberg's 1 over 4 conjecture, okay, which study the Laplacian eigenvalue, okay, on the hyperbolic space, okay. But anyway, okay. So a natural question is that can we understand the analytical properties of these more general automorphic L functions and its local factors, okay, through harmonic analysis on the group G or its related some related varieties, okay. So when we say harmonic analysis, basically we want to define some Schwarz space, okay, on the reductive group G, okay. And then we want to define some Fourier transform, okay, which intertwines this Schwarz space, okay. And finally, we want to prove some Poisson summation formula for this Schwarz space and the Fourier transform, okay. Okay. So around 2000, Braun and Kashdam, they proposed a conjectural framework to establish the analytical properties for these more general L functions, okay. And their proposal has been elaborated by Laurent Lafoque, okay, and by Baochao and Go, okay. So the general setup is very simple, okay. Basically, you just take G to be a reductive group over some global field. So throughout our talk, let's take K to be a number field, okay. And rho to be a representation of its dual group, okay. And the prototype of their proposal is the story of Theosidis and Goleman-Jacquet, okay, which applies to the case when G equals GRN, okay, and rho is the standard representation of GRN, okay. 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 So there are the following conjecture ingredients inside their proposal, okay. So the conjecture is very vague, okay. So basically, for any reductive group G and the representation of its dual group rho, okay, they speculate that there should be some row-Schwarz space, okay, which we write as S row, okay. And here P is the local place of your global field, okay, which should contain all the smooth and the complex supported functions on G, okay, and is contained in the space of all smooth functions on G, okay. Okay, and there should be a Fourier transform, okay, which is G cross G equivariant, okay, and intertwines the Schwarz space, okay. And finally, if we take gamma the summation over all the rational point of G, okay, okay, then for any global Schwarz function phi, okay, then summation gamma over gk of phi gamma, okay, is equal to the summation of gamma inside gk of the Fourier transform of phi gamma, okay, okay, okay. So this is their conjecture, okay. So this is a very vague conjecture, okay. So let's see the most basic example, okay, which is just the Goldman-Jacquet theory, okay. We take G to be GRN, okay, and the rho is the standard representation, okay. So in that case, what is the Schwarz space, okay? So we know that GRN embeds into n times n matrix, okay, open densely, okay, because GRN is just n times n invertible matrix, okay. And the n times n matrix itself is a vector space, so you have a natural candidate of the Schwarz space there, okay. So basically, we just take all the Schwarz functions on the n times n matrix, and we do restriction to GRN, okay. Okay. And because it's a vector space, you also have a natural Fourier transform, okay, there, okay. And it turns out that using these two ingredients, you can establish the analytical properties for the standard L function of GRN, okay. 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 So the general setup of Brahma-Kashtan proposal is the following, okay. So every time you have some Schwarz function, okay, right now we still don't know what is S rho, but anyway, okay, let's assume that we know what it is, okay, and take a general rho Schwarz function, okay, and take an irreducible admissible representation of G, okay, which we write as pi, okay, okay. So C here, C pi P is space of matrix coefficient, okay, and we form the following integration, okay. Okay, so this is usually called a zeta integral, okay, Z S phi 5 pi P, okay. It's the integration on the group G, okay, of the Schwarz function phi, okay, integrate against the matrix coefficient, okay. Then you do a determinant twist, okay. For instance, for GL2, you just take the determinant to the power S plus n rho here, okay. So n rho here is just the pairing between the half sum of positive roots of your group, okay, with the highest weight of your representation, okay. Okay. Okay, but anyway, okay, we just form this zeta integral, okay. Okay. Then we expect the following analytical behavior for the rho Schwarz space, okay. So for any this sort of rho Schwarz function, okay, the zeta integral should be absolutely convergent for real part of S sufficiently large, okay, with a meromorphic continuation to the whole complex plane, okay. And moreover, it should be a holomorphic multiple of this local L factor, Ls pi P rho, okay. And for P not Archimedean, okay, if you let phi runs over all the rho Schwarz function, okay, and phi runs over all the matrix coefficients of your irreducible representation, okay, then it should just be a fractional ideal of C q to the S, q to the minus S, okay. Q is the residual cardinality of your local field, okay, okay, times the L factor, okay. So in other words, this local L factor exactly captures the pose of your zeta integral, okay. And if P is Archimedean, okay, this zeta integral should be exponentially decay in any bounded vertical strip, okay, with possible pose removed, okay. And it should also be a holomorphic multiple of the Archimedean local L factor, okay. And then you have a distinguished function, usually called the basic function, okay, that is invariant under the left and the right translation action of the maximal compact subgroup of G, okay, such that it's invariant under the Fourier transform, okay, okay. And moreover, if your representation pi is unramified, okay, and you take phi P to be zonal spherical, then this zeta integral exactly gives you the local unramified L function, okay. And in particular, in the case of Goldman-Jacquet, this basic function is just a characteristic function of integer points of matrix. Okay. And what about the Fourier transform? Okay. So first, the Fourier transform should provide you the following symmetry for the local theta integral. Okay. So if we substitute s by 1 minus s, okay, and replace a phi here by its Fourier transform, okay, and the phi pi p check here is just phi pi p g inverse, okay. Then the zeta integral left-hand side, okay, after a meromorphic continuation, okay, it should just be proportional to the original zeta integral up to a constant, which we usually call the gamma function, okay, gamma s pi p rho psi, okay. Okay, so this is the rho gamma function, okay. And moreover, this Fourier transform, a priori, it looks very abstract, okay. It turns out that you can realize the Fourier transform in the following explicit style, okay. So if you let phi to be a smooth and compact supported functions inside G, okay, then this operator, okay, can be written as the following convolution, okay. So up to some determinant shift, okay, it's just a convolution of some invariant distribution on G, okay, which we write as J rho psi, okay, convolve with phi check, okay. Okay. So here J rho psi is some invariant distribution on your group G, okay, such that for any irreducible representation pi of G, okay, you can define the action of this invariant distribution on pi, okay. So a priori, this action is definitely not well defined because everything is non-compact, okay. But there should be a way to regularize it, okay, such that the action of this distribution on the irreducible representation exactly gives you this gamma function, okay. So you see that left-hand side, because you have some invariant distribution, also some invariant function, okay. So by sure lemma, formally, its action on any irreducible representation should give you some scalar, okay. So what is a scalar? It should exactly be the non-standard Lorentz gamma function here, okay. And just like the usual Fourier transform, okay, this non-standard Fourier transform should also extend to a unitary operator on the L2 space on G, okay. And if you apply it twice, okay, you just get identity, okay. And in particular, in the case of GLN, what is and the rho standard, okay, in the classical story, what is the Fourier kernel here, okay, J rho psi, okay. It's just the usual additive character composed with trace, okay. Just the usual exponential function, in other words, okay. Okay, so in other words, our Fourier kernel here should be a non-trivial generalization of the usual exponential function, okay. Okay. So our goal, our talk today mainly focuses on the invariant distribution J rho psi. Okay, as you can expect, this is one of the most essential ingredients in this conjecture. Okay, so there's also a finite field analog of this invariant distribution. Okay, and basically you just work with something like character shifts. Okay, and then Brown and Kashdan they gave a conjecture construction first. Okay. And then in the case of semi-simple rank 1, okay, they verify that their construction is correct, okay. And later, Chen and Ngo show that if G equals GLN, okay, then their construction is also true, okay. And Chaoxian Chen verified the conjecture for finite fields with large residual characteristic and a D-module setting, okay. And the Lamont-Latter, they gave an explicit verification for their conjecture, okay, over any finite field, okay. Okay, so it turns out that over local fields, the understanding for this kernel is still pretty limited. Okay. Okay. So in my joint work with Jiang and Zhang, okay, we give an explicit formula when G is the symplectic group and rho is the standard representation of the symplectic group. Okay. So you take G to be SP2N, actually you need to work with GM cross SP2N, but anyway, okay. And the dual group of SP2N is SO2N plus 1C, okay. And look at the standard embedding of SO2N plus 1C into GL2N plus 1C, okay. 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 And then in that situation, we give an explicit formula for the Fourier kernel, okay. In later slides, we will see that formula explicitly, okay. And in my work with Ngo, okay, if G is abelian, okay, we show that this kernel is represented by a smooth function on the group G, okay, and it enjoys all the desired properties, okay. Okay, and if G equals SL2 or GL2, okay, and if the residual characteristic is not equal to 2, okay, we provide an explicit integral formula for the kernel, okay. But today we will mainly focus on some algebraic behavior in our F to be a p-adic field, okay, and let's take G to be Gm cross SP2n, okay. So as we said, the dual group of G is just C cross, okay, which is the dual group of Gm, okay, cross SO2n plus 1, okay, C, okay, which is a dual group of SP2n, okay. Then you have a standard embedding into GL2n plus 1C, okay. So here C cross just acts by scaling on GL2n plus 1, okay. And then we can give a full description of the Rho-Schwarz space in this situation, okay, through the geometry of a singular reductive monoid attached to G, okay, with unit group. So what is the Fourier kernel? Okay, so for any A and a G inside F cross cross SP2n F, okay, then its kernel is literally just given by a function, okay. So it's the integration, okay. So this integration is not absolute convergent, okay, but there's a way to regularize the integral, okay. It's the integration of F cross n copies, okay, and the usual exponential function per psi here, okay, and A times determinant for emphasis G plus I to n, okay, over product I from 1 to n of y squared, okay, plus summation I from 1 to n of yi for emphasis. And here product I from 1 to n, absolute value of yi to the power minus of 2i plus 1 dyi, okay. So in other words, this Fourier kernel behaves something like for instance, like the Kuzma integral kind of thing, okay. But it's a little bit more complicated, okay. Okay, then let me briefly explain my joint work with Ngo, okay, on the construction of non-abelian Fourier kernels for SL2 and GL2, okay. Okay, so there are the following essential ingredients appearing in our work, okay. So first we define the so-called Laforgue transform, okay, connecting the so-called stable Bernstein center of the reductive group G, okay, and the so-called stable Cashton cocenter, okay. And then we need to use the so-called Lagrange stable transfer, okay, connecting the stable cocenter of G, okay, and the stable cocenter of its maximal tori, okay. So in particular, in the case of SL2 and GL2, okay, it goes back to a classical work of Gelf and Graef for the stable character formula for SL2, okay. And in the case of SL2 and GL2, it turns out that both transforms can be realized as simple integral transforms on the so-called Steinberg-Hitchin base of G. Okay. So let's first recall the notion of Bernstein center. Okay. So if you have a finite group G, okay, then for the so-called center, basically you just look at the center of its group algebra. Okay. Then because the group algebra of a finite group G, okay, can be written as the direct sum over all the irreducible representations of G, okay, then you look at the endomorphism ring of the representation, okay. Therefore, the center for the finite group ring, okay, it is equal to the direct sum of one-dimensional vector space parameterized by all the irreducible representations, okay. So over non-Archimedean situation, okay, the Bernstein center they have several equivalent categorizations, okay. But in our talk, we only need to use the following two equivalent categorizations, okay. So on one hand, it can be identified as invariant. Here, I mean conjugation invariant, okay. And essentially compact supported distributions on the group G, okay. Here, a distribution is called essentially compact supported if its convolution with any test function is still a test function, okay. And Bernstein showed that this algebra, okay, admits the following spectral characterization, okay. It can also be realized as the regular functions on the so-called Bernstein variety of the group G, okay, which are irreducible representations of G up to inertial equivalence, okay. Okay, basically, they are just parameterized by the Caspito support of the irreducible representations of G, okay. Okay. And we introduce the following subring, okay. ZG finite, okay. This is a non-unital subalgebra, okay, supported on only finitely many connected components of the group G, okay. And then we have the so-called stable Bernstein center, okay, which is just a subset of the usual center, okay, consisting of stable distributions, okay. Okay. If you work with GL2, you can just forget about the notion of stable center here, okay, but anyway, okay. Okay, then let's briefly introduce the notion of Cauchy-Don cocenter, okay. So in the case of finite group, okay, you have the group algebra of your group G, okay. Then the cocenter, as the name suggests, is just CG modulo its commutator, okay. So for non-Archimedean case, okay, the idea is similar, okay. So the usual cocenter is just H here is smooth and the complex supportive functions on G, okay, the usual Heck algebra, okay. Then the cocenter is just the usual Heck algebra modulo its commutator, okay. Okay. Then a theorem, I believe due to Cauchy-Don, tells you that this cocenter can be identified as the space of optical integrals on G, okay. Okay. And it turns out that you can also realize these space as functions, some sort of algebraic functions on the variety of irreducible representations of G, okay. So it turns out that irreducible representations of G, okay, has a variety structure, a complex variety structure, okay. This is what is called the Laforgue variety introduced in the work of Pythagoras, okay. And the Trace-Palomino theorem, due to Bernstein, Deligne, and Cauchy-Don, tells you that functions on irreducible representations of G with suitable algebraic condition and the finite support condition, okay, is exactly identified with the usual cocenter of your reductive group G, okay. And the stable cocenter, this is nothing surprising. It's just the stable optical integrals of smooth and the complex supportive functions, okay. Okay. And the Laforgue transform is defined as follows, okay. So every time so first this is just a linear transformation, okay, from the cocenter to the center, okay. And every time we have some element inside the cocenter, okay, we know that it can be identified as optical integral of some test function, okay. So we can pair it with the distribution character of some admissible representation, okay. So in particular, if we pick up any point inside the Bernstein variety of G, okay, so here M is a levy of your reductive group G, okay, and the sigma is a supercuspal representation of your group G, okay. So if you take G to be GL2, okay, you can take M to be the diagonal torus, okay, and sigma is just some character, okay. And we just look at the pairing between the optical integral of some test function, okay, with the distribution character of this induced representation, okay, induced from the levy to G of this supercuspal representation, okay. Okay. Okay, then indeed this is a regular function, okay, by the Trace-Palomino theorem, okay. And in particular by the spectral characterization for the Bernstein center, okay. You know the image indeed lands inside the center of G, okay. Okay, so this is a purely representation theoretic map a priori, okay. But it turns out that we can show if G is equal to SL2, okay, and the residual characteristic not equal to 2, okay, then this purely representation theoretic map, okay, can be written as a simple analytical formula, okay. So precisely we show that the Laforgue transform has a section, okay, from the center, okay, to the subspace of the cocenter that are perpendicular to the trivial representation, okay. In other words, we are looking at the optical integral of test function, okay, so that its pairing with the distribution character of trivial character is equal to 0, okay. Okay. And second, for any distribution J inside the stable finite part of your center, okay, this distribution can be written as the pullback of some function JC on the affine line, okay, and along the trace map, okay, times the Haar measure dg, okay. So SL2, okay, you have a natural map to the affine line, okay. Basically, you just take the trace map, okay. Then you just pick up some function on the affine line and you put it back along the trace map. You get some conjugation invariant, actually stably conjugation invariant functions on SL2, okay. Then for some very nice function JC, it will provide you with some stable distribution in the Bernstein center, okay, with finite support condition, okay. Then you can show that this function on the affine line, okay, is absolutely integrable, okay. And then if you take the classical Fourier transform, okay, because on the affine line you have a classical Fourier transform, then this function is globally bounded, okay, and smooth, and vanishing at 0, okay. And in particular, if you take its Fourier transform, and you divide by the absolute value norm, okay, on the alpha line, and you do Fourier transform back, okay, then it realizes the section for your Lafourcade transform, okay. Okay. So a priori, upstairs you get some purely representation theoretic map, okay. It turns out that if you look at the stable locus of this map, okay, and you put some constraint like this distribution is actually a function, okay, then this map can actually be written by this simple analytical formula, okay. Okay. So in particular, in the real field, this formula actually recovers a classical relation between Chebyshev polynomials of first and second kind, okay. Okay. Then let's briefly recall the notion called the Lennard stable transfer, okay. So every time we have two reductive groups, H and G, okay, we have its dual group LH and LG, okay. Okay. And let rho be a group homomorphism from LH to LG, okay. So for instance, you take H to be GL2, okay, G to be GLn plus 1, okay. Then you can take rho to be the symmetric nth power, okay. Then the Lennard stable transfer is a lifting of stable distribution characters from those stable distribution character of H, okay, to the stable distribution character of G, okay. So the reason is that, I mean, by Lennard's functoriality, or say local Lennard's correspondence, every time you have a map between two L groups, okay, it predicts a lifting from the L packets, or say the irreducible representations of H, okay, to the irreducible representations of G, okay. So in particular, that association gives you a lifting of stable distribution characters of those representations of H to those of G, okay. And dually, okay, because the stable optical integrals, in some sense, they are dual to the stable characters, okay. Therefore, this association, okay, provides you a transfer of stable optical integrals of G, okay, to the stable optical integrals of H, okay. And Lennard himself analyzed the case of when G is equal to SL2, okay, and then H is the maximal torus, okay. So it turns out that in that case, this transfer goes back to a simple formula discovered by Gelf van der Graaf in 1963, okay. So the maximal torus inside SL2 up to stable conjugacy, okay, they are parameterized by quadratic algebras of your local field F, okay. So every time you have quadratic algebra E over F, okay, it provides you a maximal torus inside SL2, okay. Then what is the stable transfer from stable optical integrals on G to stable optical integrals on inside E1? Okay, so E1 is a maximal torus inside SL2, okay. Then if we, I mean, as we said, stable optical integrals on SL2 can be identified as functions on the affine line, okay. Then we take the classical, I mean, affine line, again, we have a classical Fourier transform, okay. We take its Fourier inversion, okay. Then multiply the quadratic character for this quadratic algebra, okay, eta E, okay. Then do Fourier inversion back, Fourier transform back, okay. There's some constant in front, but let's forget about it, okay. So basically, we just do similar operation like the Lafourcade transform that we have seen before, but we just substitute the absolute value by the quadratic character, okay. Okay, then this simple formula realized the stable Lennard stable transfer, okay, okay. From the group G SL2, okay, to its maximal torus, okay. Any quadratic algebra here, okay. Okay. So in particular, for the non-abelian Fourier kernel that we really care about, okay, so the Fourier kernel J rho, okay. So first, we expect that this Fourier kernel is represented by some function on the affine line, for instance, for SL2, okay. And then for this function, okay, if you apply the Lafourcade section, okay, to this function on the affine line, okay, then apply the stable transfer to this function, okay. Then we will get a collection of distribution, let's write it as J rho E psi, okay, parameterized by the quadratic algebra E over F, okay. Then it turns out that these distributions, they are literally just functions on the maximal torus, okay. And these functions are purely of abelian nature, okay. So in other words, after some algebraic steps, okay, simple analytical steps, let's call it, okay. Then for this non-abelian object, okay, we produce some abelian object, okay. Then from this abelian object, we can reproduce the Fourier kernel here, okay. So let's see how many times we have, okay. So let me write something on the whiteboard, okay. So we have the stable center here, okay. Let's take G to be SL2, okay. Then from the stable center here, we have a Laforgue section, as we mentioned, okay, to the stable cocenter, okay. Then we have the stable Lennard stable transfer for any quadratic algebra T, okay, to the stable cocenter of your maximal torus, okay. So our Fourier kernel, okay, up to some simple modification, you can show that it lands inside the stable center here, okay. Okay. Then you apply this Laforgue section, okay, which is the map like taking classical Fourier inversion, okay. Then divide by the absolute value norm, okay, and then do Fourier transform back, okay. Then you produce some function, let's write it as J rho psi prime, okay, inside here, okay. Okay, then you apply the stable transfer, which is you take Fourier inversion, okay, and then multiply by the quadratic character, okay, and do Fourier transform back, okay. Okay, and restrict to the image of trace E1, okay. Then you get something purely abelian here, okay. Then from this datum, okay, so here now we have some abelian datum, okay. Then from this abelian datum, we can reproduce the original Fourier kernel that we want, okay. Okay. Okay, so precisely, we have the following formula, okay. So J rho psi here, okay, is equal to, so here you have the Laforgue transform, okay. So this is the Laforgue transform, okay. Then for each J rho E here, we show that there's a distinguished section which we write as curly E, okay. Okay. Apply to this J rho E here, okay. And you sum over all E over F, okay. Okay. Okay, then we just get a formula for the Fourier kernel, okay. 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 So this is the final formula, okay. So far, okay. 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 Here, residual characteristic is not equal to 2. Okay. Okay. And it turns out that similar phenomena also shows up when you study the so-called Opto-Henkel transform on the group. But I don't think we have enough time, okay. So I think I will just stop here. Yes, thank you.
Thanks for a nice talk. Any question?
Yeah.
So your result with angle for GO2 or SO2 is for any row?
Any row, yeah.
Any row you can get these kernel functions?
Yeah.
And also, can you define the Schwarz space in this case?
Not so far, yeah, no.
Or do you have any conjectural kind of? Is it enough to just take the complex supported function and then you also apply the Fourier transform?
In the case of Goldman-Jacquet, that's not enough. That's false, yeah.
That's okay. That's true.
That's false.
Oh, it's false.
Yeah, it's false, yeah.
Okay.
So in the case of Goldman-Jacquet, you can show that Schwarz functions on matrix is not equal to CC infinity on the group G plus the Fourier transform. Yeah, even in non-Archimedean, Archimedean of course false, but even in non-Archimedean, it's still false. Yeah, yeah, you can prove it actually.
Okay. And also, do you know your Fourier transform preserve the basic function?
Yeah. That just follows from the definition of gamma function.
Further questions? If no, let's thank speaker again. Next talk will be 15 minutes. pleasure to have Jiepeng Fang from the University of Hong Kong, and he will tell us about positivity properties of canonical basis.
Thanks for the introduction. It's my pleasure to give a talk here. Today, I will talk about the positivity properties of a canonical basis. This is based on a joint work with Professor Xuhua He. Firstly, let me introduce some background on quantum group and the canonical basis. We face a symmetric quantum datum, I dot, where I is a finite set, and the dot is a symmetric bilinear form on the free abelian group generated by I. And we face a Y regular root datum, YS, and of type I dot, where Y is the co-weight lattice and S is the weight lattice. And for any natural numbers, and we denote this element in the field of rational functions in V. And the quantum group U is the QV algebra with the unit generated by Chevrolet generators EI, Fi, and K mu for any I in I and mu in Y, and subject to the following relations, where the subalgebra generated by all this K mu is the group algebra of this co-weight lattice Y, and this K mu and the EI, Fi satisfy these commutative relations. And the commutative relations of EI and Fj is equal to delta Ij and Ki minus K minus I over V minus Y V inverse. And the last two relations are the quantum style relations. And the quantum group is a Hopf algebra. It is a deformation of the universal enveloping algebra of the Kazhimoudi-Lie algebra, defined by this root datum. And the quantum group has triangular decompositions. It is, as a vector space, it is isomorphic to the U plus tensor with U0, tensor with U minus, where the U plus and is the subalgebra generated by EI, and the U0, the garden part, is the subalgebra generated by K mu, and the negative part, U minus, is the subalgebra generated by Fi. And the positive part, U plus, and the negative part, U minus, are isomorphic. And for convenience, we follow the notations in Lu Siddiq's book, Introduction to Quantum Group. We introduce the algebra F. It is the QV algebra with the unit generated by theta I and subject to the quantum style relations. And by definition, we know that this algebra is isomorphic to the positive part, U plus, and also isomorphic to the negative part, U minus. We denote these isomorphisms by the image of S in F is denoted by S plus, and the second isomorphism, the image of S is denoted by S minus. And then this isomorphism gives that the Chevrolet generators EI is equal to theta I plus, and the Fi is equal to the theta I minus. And the canonical basis is introduced by Lu Siddiq. It is a basis of this algebra F, and as well as the basis of the positive part or the negative part. And this basis subsequently also introduced by Kaswala, known as the global crystal basis. And this basis has very remarkable properties. And the first one is it is an integral basis. And that is the integral form of the algebra F is the GVV inverse subalgebra generated by these divided powers. And the canonical basis is an integral basis of this integral form. And also, this algebra has a bar involution. It is a Q algebra involutions defined by the generators is fixed by this bar involution. And the bar of Vn is V minus n. And the canonical basis elements are bar invariant. It is fixed by these bar involutions. And the algebra F has a non-degenerate symmetric bilinear form. Then these bases satisfy the almost orthonormal property. And the most important property is the positivity of the canonical basis. That is, given two base elements, B and B plus, B and B prime, if we write their product, B prime, in the linear combination of the canonical basis, and then the coefficients belong to NVV inverse. That is the Laurent polynomials with coefficients with non-negative coefficients. And also, for the co-multiplication R, for the canonical basis elements B, if we write its co-product into the linear combinations of canonical basis of the tensor product of canonical basis element, and the coefficients also belong to NVV inverse. This is the positivity properties of the canonical basis of the algebra F. And Lustig proved these properties by the categorization of this algebra by power shifts on the modular space of Q representations. And the canonical basis also has a very good property. It will give the basis of the simple lowest ring module or the simple highest ring module. And we denote it by the S plus to be the subset of the dominant weights. And for any dominant weight lambda, we denote by lambda to be the simple highest ring modules with the highest ring vector eta lambda. And the omega lambda to be the simple lowest ring module with the lowest ring vector c minus lambda. And Luz proved that the canonical basis of the algebra F, that is B, and as well as the canonical basis of the negative part, that is the canonical basis elements B minus. And if we take the action of this B minus on the highest ring vector eta lambda, and those non-zero elements form the basis of this simple highest ring module. And Lustig defined it to be the canonical basis of this module. And this basis also has very remarkable properties, which is also an integral basis. The base elements are also bi-invariant, and it also satisfies the almost orthonormal property. And Lustig also proved that the canonical basis of the module also has a very good positivity properties. That is, the action of the Chevrolet generators EI, Fi, given by the corresponding matches of the action of the Chevrolet generators EI and Fi. Their entries are also belong to the NVV inverse. This is the positivity properties of the canonical basis of the module. And similarly, the lowest ring module, omega lambda, its canonical basis is given by the canonical basis of the U plus, that's it, the B plus. If we take the action of B plus on the lowest ring vector c minus lambda, and those non-zero vector give a basis, and this is the canonical basis of the lowest ring module. And this canonical basis also has similar properties as well as the canonical basis of the highest ring module. And then in representation theory, it is natural to consider the tensor product of two modules. And for any two U modules, M1 and M2, their tensor product over the as a vector space is naturally a U tensor U module. And then we restrict it to be a U module by the co-multiplication of the quantum group, delta. And then given two dominant weights, lambda 1 and lambda 2, and the tensor product of the lowest ring module and the highest ring module, this tensor product naturally has a basis given by the tensor product of the canonical basis. But this basis is not good enough because the bar evolution on the tensor product is not compatible with the bar evolution of the quantum group at the action of the quantum group. That is, we don't have the action of U on M1 tensor with M2. Then we take the bar evolution on the tensor product. It's not equal to the bar evolution of the quantum group U bar as on the tensor product on the bar of M1 and M2. Because the co-multiplication of the quantum group does not commute with the bar evolution of the quantum group. And to fix this problem, Lustig defined a new evolution on the tensor product, and such that this new evolution phi is compatible with the bar evolution of the quantum group and the action of the quantum group on the tensor product. This is so-called phi evolution. It is defined by the quasi-R matrix, which is analog to the universal R matrix introduced by Greenfield. And then he proved that the tensor product has a new basis. The base elements is denoted by these notations. The canonical basis element of the Lewis ring module B1 plus as of the Lewis ring vector, and the diamond, and the canonical basis elements B2 minus as on the Lewis as on the high ring vector. And this base element is phi invariant with respect to is fixed by this new evolution, the phi evolution. And then he defined it to be the canonical basis of the tensor product. That is, the canonical basis of the tensor product that does not coincide with the tensor product of the canonical basis. And more generally, Lustig and later Quantenbaum and Weiqiang Wang generalized both results and defined the canonical basis of the tensor product of a sequence of Lewis ring module with a sequence of high ring module. And then there is a natural question: does the canonical basis of the tensor product has the positivity? We know that Lustig proved that each Lewis ring module has the positivity. The canonical basis of each Lewis ring module has the positivity, and the canonical basis of each high ring module has the positivity. But the canonical basis, the tensor product of the canonical basis naturally have the positivity. But the canonical basis of the tensor product is not the same as the tensor product of canonical basis. And so this question is a very natural question, but it is very difficult. And there are only some positive answers in some cases. In finite type A, based on the works by Burleson, Lustig, and Mathematicians, they proved that the action of the canonical basis element of the modified quantum group. I will introduce the modified quantum group, and there is canonical basis later. They proved that these actions has the positivity. And for iPhone type A, based on the works by Lustig, Ginzburg, Schiffman, Wasserott, and Fu and Shoji, they also proved that the action of the canonical basis element of the modified quantum group has the positivity. And for any symmetric quantum datum, if we also only consider the tensor product of Lewis ring module or the tensor product of high ring module, that is M is 0 or N is 0. And Webster and also my earlier work with Yixin An we prove that the tensor product of this the canonical basis of this tensor product have the positivity. We prove that the transition matrix between the canonical basis of the tensor product and the tensor product of the canonical basis, this transition matrix has entries belong to NV inverse. And we also prove that the action of the Chevrolet generator, EI and FI, has the positivity. And the more important cases involves mixed tensor products containing both simple low swing module and high swing modules. Because this kind of canonical basis has very nice stability property when lambda increase. And they can be glued together to be the canonical basis of the modified quantum group, which I will introduce later. And our first main result proved that the canonical basis of the tensor product have the following positivity. That is, the transition matrix of the tensor product of the canonical basis of the tensor product and the tensor product of the canonical basis have this positivity. And we also proved that for any spherical parabolic canonical basis element of the modified quantum group also has the positivity. And I will introduce the spherical parabolic conditions later. And in particular, we know the canonical basis of U plus, that is B plus, and U minus, B minus. These canonical basis elements are spherical parabolic, and we know that their action has the positivity. And in particular, for the finite type, and every canonical basis element are spherical parabolic, and we prove that their action has the positivity. And now I want to introduce the modified quantum group and its canonical basis. And the modified quantum group is also introduced by Lustig. It is a QV algebra, which is a modified form of the original quantum group by replacing the Gardner part U0 by these direct sums. And for each element on the weighted lattice X, zeta, we give a one-dimensional vector space QV1 zeta. We replace the Gardner part U0 by these direct sums. And for the repetition theory reason, this algebra is better than U for the study of weight U modules. And Lustig proved that this modified quantum group U dot has a basis B dot. The basis elements are denoted by B1 diamond zeta B2, where zeta is the element in the weighted lattice X, and the B1 and the B2 are two canonical basis elements of the algebra F. And this basis has a very good property. That is, given a base element, if we take an action, take an action on the tensor product of the lowest wave vector and the highest wave vector, we will get the canonical basis element of the tensor product of this lowest wave module and the highest wave modules. And in particular, the canonical basis of B dot of the modified quantum group U dot, it is a generalization of the canonical basis of the positive part or the negative part. That is, the B minus 1 zeta is equal to 1 diamond zeta B, and the B plus 1 zeta is equal to B diamond zeta 1. And this is a very nature question, and also is a very famous and important conjecture given by Lustig. Because we know that the canonical basis of the positive part of the negative part has the positivity with respect to the multiplication and the co-multiplication. And then it is naturally to consider the positivity of this B dot of the modified quantum blue U dot. Lustig gave a conjecture. And this conjecture has more than 30 years. And there are only some cases we know that conjecture hold. For finite type A or alpha type A, and also based on the work by Burleson, Lustig, Macpherson, and Lustig, Ginsberg, Schiffman, Wasserott, Fu, and Sorgi. Based on their work, we know that the canonical basis B dot has the positivity with respect to the multiplication. And Zhao Bingfang and Yi Qiangli prove that in these cases, this canonical basis B dot has the positivity with respect to the co-multiplication. And in particular, for the finite type, and Webster proved that the canonical basis has the positivity with respect to the multiplication, and as well as the action on arbitrary tensor products of simple modules. And all this result based on the categorification theory, which based on the geometric bipolar shifts or Queer-Hacker algebra, and they are highly non-trivial. And our second main result, we prove that the canonical basis B dot of the modified quantum group U dot has the positivity properties. We prove that given two basis elements, if one of them is a spherical parabolic, then we prove that their product has the positivity. And also, for any spherical parabolic canonical basis element B dot, we prove that the action on arbitrary tensor products has the positivity. And furthermore, in particular, for the finite type, and in this case, any canonical basis element is a spherical parabolic. And so we prove that the canonical basis has the positivity with respect to the multiplication, and as well as the action on arbitrary tensor product of simple modules. This is our second main result. And our strategy is given by algebraic methods, which we call the synchroning constructions. Firstly, let me sketch our strategy. Firstly, the simple lowest ring module is the direct limit of its dimensional submodules, and which I will introduce later, the definitions of the dimensional modules. And then we reduce our result, the canonical basis of the tensor product of the lowest ring module and the highest ring module to the canonical basis of the tensor product of this dimensional submodule and the highest ring module. And we know that this tensor product is a quotient of is a U minus quotient, U minus module quotient of the tensor product of a Wehrmann module and this highest ring module. And then we will introduce this very big commutative diagram, which we call the cycling conjunctions. We can embed this tensor product of the dimensional mod of the Wehrmann module and the highest ring module into the negative part of the larger quantum group U tilde. And then we know, because we have known that the negative part of the quantum group has the canonical basis, and so we can obtain the desired positivity result from the positivity of the canonical basis of the U minus part of a larger quantum group. Now, I want to introduce our our cycling realizations. And firstly, for the Gaussian datum I dot, we define the cycling Gaussian datum I tilde dot, where I tilde is obtained from I by adding a copies of I. We denote it by I prime. And the bilinear form dot is extended from the original one by I and j prime is equal to minus delta ij. And I prime and j pi is 2 delta ij. And in the language of generalized Gaussian matrix, if the generalized Gaussian matrix of the original Gaussian datum is given by C, and then the generalized Gaussian matrix of this larger Gaussian datum is given by C tilde, which is given by this matrix. And in the language of this cos diagram, we have this example. If we have the A1, A2, and A3, and SR, and the others, and we will get A2, A4, and E6, and more other cases. And similarly, for the root datum YX, we have the second root datum Y tilde, S tilde. It is Y tilde regular root datum of type I tilde dot. Then for this second data I tilde and Y tilde S tilde, we have the corresponding algebra F tilde and U tilde. And the nature embedding from I to I tilde induce sub-algebra embeddings from F to F tilde and U to U tilde. And then for any dominant weight lambda, because we requires for any distinct I prime and J prime in I prime, and the I prime dot J prime is 0. And so theta I prime commuted with theta J prime. And so this element is, is independent of the order in the product. And then for any element in the weight lattice zeta and the dominant weight lambda, we can regard them as an element of S tilde, the larger weight lattice by the nature embedding. And then we define the second product denoted by theta, zeta, O dot lambda, defined by these equations. In particular, now we take the zeta to be the minus extreme weight. That is given to dominant weight lambda and the lambda 1 and the lambda 2, and the element in the Y group W. And we take the signaling product of this minus extreme weight minus W lambda 1 and the lambda 2. It is element in the weight lattice at S zeta. And then we take the Werner module of the bigger quantum group U tilde with this highest weight. And then it is a U module by the nature embedding. And we prove that the subspace spanned by S theta lambda, this is a type of S theta lambda 2 Y. The subspace spanned by this element is a U submodule of this bigger Werner module. And then we construct two U module isomorphisms from this subspace F theta lambda 2 F and the tensor product of this Werner module and a simple high-3 module. That is, we have two U module isomorphisms, and they are inverse to each other. And we take the UB minus to be the sub-algebra generated by K mu and Fi. And then we take the minus W lambda 1 to be the unique canonical basis element of the weight minus W lambda 1. And then the de major module is the UB minus submodule of the lowest weight module generated by this extreme weight vector. And we can prove that there is the surjective UB minus module homomorphisms from the Werner module to this the major module, given by the action map. S minus 1 maps to S minus C minus W lambda 1. And this is kernel is this annihilator. And then we take the F tilde, this one to be the left ideal of F tilde generated by this annihilator. And we defined this left ideal is a UB minus submodule of this subspace. And then we define a UB minus quotient to be this subspace respect to this intersection. And we denote by the pi to be the nature projection. And then we prove that these two U module has homomorphisms between this subspace to the and the tensor product of the Werner module and the high-speed module, factored through the quotients of this one and to the tensor product of the de major module and the simple high-speed module. And that is, we realize the tensor product of the simple lowest of the de major module and the simple high-speed module as a quotient of this one. And this one, by definition, is a subspace of the negative part of a larger quantum group. And this is our cycling realizations on the model level. And then we also proved that this realization is compatible with the canonical basis. Firstly, we can construct the canonical basis of the tensor product of this Werner module and the high-speed module by the same method given by Lustig and Kuang Bao and Weiqiang Wang. And then we take the canonical basis B tilde. This is the canonical basis of the larger algebra F tilde. And we can prove that the intersections, this intersection is a basis of this subspace. That is, we have this a basis of this subspace. And then we can prove that these intersections give the basis of the tensor product of the de major module and the high-speed module. And finally, we can prove that these base elements, if we take the nature projections, those non-zero elements will give a basis of these quotients. And this property is similar to the canonical basis of the negative part. That is, the canonical basis of the negative part as on the high-speed vector. Those non-zero elements will give a basis of the simple high-speed module. And this property is similar to this one. And then we have our signaling realizations on module level. That is the commutative diagram in the middle one. It is compatible with the canonical basis we constructed before. That is, these maps are inverse to each other, and they restrict to the bijections between the bases. Finally, I want to introduce how the signaling realizations induce the positivity result. Because the direct limit of the de major submodule is isomorphic to the lowest weight module, to the whole lowest weight module. And we have this cycling realizations. And also, for any canonical basis elements in the tensor product of the lowest three module and the highest three module, we can find W in the Y group. And then it is a base element of this tensor product of the dimensional module and the high three module. And then we can find a B tutor in this one, the base element of this subspace B tutor, such that the canonical basis element is given by phi prime, pi, and B tutor. And then this phi and pi is a UB minus module homomorphism. And so for any B in of the B in B, the canonical basis of the algebra F. And so we have B minus, the canonical basis element of the negative part. And we know that the action of B minus on this element is equal to this one. And by the positivity of the, and we know that B minus is a canonical basis element of the negative part, and the B tutor is a canonical basis of element of this subspace, and it is also the it is also a basis element of the negative part of the larger quantum group, and so by the positivity of the B tutor, we know that B minus B tutor has the positivity. And so we know that this action has the positivity. And then for the action of B plus, we can prove that the B plus on this tensor product can be transferred to the action of B minus on this one. Notice that it is the lowest three module with the lowest three minus lambda 1 and the highest three module of the highest three lambda 2. And this is the lowest three module with the lowest weight minus lambda 2 and the highest three module with the highest weight lambda 1. And then we have proved that the action of B minus on this one has the positivity. And so the action of B plus on this tensor product also has the positivity. Then we have proved that the action of B minus and the B plus has the positivity. We want to know whether the action of arbitrary canonical basis element in B dot has the positivity. Unfortunately, because our homomorphism phi and pi is a U minus module homomorphism, it may not commute with the action of EI. And we need technical conditions. That is, for W in the Y group and I with SIW less than W with respect to the Broad order. And we know that this tensor product of the dimensional module and the high three module is stable under the action of this EI, the Chevrolet generators. And this UB minus model homomorphisms also commute with the action of EI. And for this technical condition, SIW less than W, we need to introduce the conditions we call the spherical parabolic. And for the subset J, we let WJ to be the subgroup of the Y group generated by SJ, and we call it is spherical if this subgroup is a finite group. Because if it is a finite type, and we can take the longest element W0, which satisfies SIW0 less than W0. And then for the spherical subset, we can define a parabolic subalgebra. The parabolic subalgebra Uj dot is of U dot is generated by this one. It's the uj plus tensor with u minus op submodule of u dot generated by this one. And similarly, we have the opposite parabolic subalgebra. And then we can define the so-called spherical parabolic subalgebra. And the base element in the modified quantum group is called a spherical parabolic if it is contained in some spherical parabolic subalgebra. And then we can prove that our first main result, the positivity of the canonical basis of the modified quantum group. Given two canonical basis elements, if one of them is spherical parabolic, then their product have the positivity. And also for the any spherical parabolic element, and the action of its action on the tensor product of the lowest ring module and the highest ring module has the positivity. And in particular, for the finite type, and any canonical basis elements are spherical parabolic, and so we have the positivity with respect to the multiplication and the action on the tensor product of one lowest ring module and one highest ring module. And then both results can be generalized to be the tensor product of several lowest ring module and several highest ring module. And we can prove that the transition matrix between the canonical basis of the tensor product and the tensor product of the canonical basis has the positivity. And also, for any spherical parabolic element, B dot, we can prove that its action has the positivity. And in particular, the canonical basis element of U plus or U minus are spherical parabolic. And so their action has the positivity. And in particular, for the finite type, and we can prove that its action on arbitrary tensor product of simple modules has the positivity. And this is all of my talk. Thank you very much.
Thanks for a nice talk. Any questions?
Page 5.
So I'm wondering, suppose, is the canonical basis, up to some permutation, the unique basis that satisfy these properties together with the positivity on this slide? Is the canonical basis the unique basis that satisfy?
Yes. It is the up to a sign. The canonical basis is the unique basis which is integral bar invariant and have the almost orthogonal.
Oh, you mean these three are already enough for the uniqueness?
No, it is up to a sign.
Of course, after a sign.
After a sign.
Yeah.
But the positivity property requires the sign must be a plus, not a negative one.
I see. Thank you.
Further questions? May I ask, what's the main applications for these positivity properties?
There is an application given by the total positivity. Yes, Lucy defined the total non-negative part of a reductive group or the flag variety, and it is very important relations between the positivity of the canonical basis. And the total positivity result is one of the important motivation of the cluster algebra introduced by Fermi and Jalovinsky.
Thank you. Any further questions? If no more, let's thank speaker again. We will resume in 15 minutes.
center of that universal enveloping algebra. Following the definition, following McDowell and Mathematicians, we can define a Witten module. So in this setup, finitely generated G module M is called Witten module if the action of UG n, UN, n is a new radical, and the center of even parts are locally finite. So for example, modules from the BGG category O are all Witten modules. And the first example of non-weight simple Witten module was discovered by Arnold Pinkerton for SL2. So for SL2, any simple non-weight Witten modules arise from extending the regular H module. So this means the universal enveloping algebra of the Cardan subalgebra can be extended to SL2 module, and we can classify a simple Witten module this way, non-weight simple Witten module. So there are some classical results for Lie algebra case. Arnold Pinkerton initiated the study of simple Witten module for SL2, and Coulson put it in a more general context. And McDowell, Mathematicians, and Becklin systematically study Witten modules for general case, which I will expand in more detail in this part. In the study of Witten modules, the concept of Witten vectors plays an important role. Let n denote the category of all Witten modules corresponding to the triangle decomposition. And we set the set of all characters of even new radical to be CH0 bar. And then for each such a character, we can define for each Witten module the subspace of Witten vectors. So this is a definition of Witten vectors for a Witten module M. So a Witten vector, by definition, is a vector which spans the one-dimensional character theta. So we denote the Witten subspace, Witten vector subspace of Witten module by WH subtheta of M. Then the category of all Witten modules M has a decomposition into direct summates and theta, where theta runs over characters of even radical. Here, n theta is a full subcategory of Witten modules generated by Witten vectors associated to theta. So fundamental question is to ask how to classify simple objects in n theta. So if we have such a decomposition, then we may focus on each Witten block n theta. For example, if theta is 0, then N0 is just the category of finite length G modules whose composition factors are all Heisman modules. So N0 contains ordinary BGG category O, and so our question about classification of simple objects here can be answered. So in this Witten block N0, all simple objects are just simple Heisman modules. For reductive Lie algebra, the extreme case is given by Coulson's non-singular Witten modules. So now suppose that G is a reductive Lie algebra. And we choose a character to be theta to be non-singular, by which we mean the kernel is the dimension of kernel is minimal. We have just seen the case when theta is 0, which has maximal kernel. So this is another extreme case. Let's denote the category of finite-dimensional modules over the center by ZG-FD mode. Then for each finite-dimensional module over ZG, we may extend, so each object in this category, we may extend it to a module over the product ZG UN by letting n theta x trivially. Here n theta is shifted. Here n is, we recall that n is neo-radical from a triangle decomposition. N theta is a shifted version of this neo-radical. We let n theta x trivially. So V is ZG module, and the action is given by the character. So x act via the character theta. Then in this case, in this setup, Cosson proved the equivalence of categories from n theta. So this category n theta to the module finite-dimensional module category of the center ZG. The equivalence is given by the function of taking Wien-Take vectors, and the quasi-inverse is given by induction. Here, we extend ZGF mode, objects in ZGF mode to be objects over ZG UN. Then we induce to be a ZG module. So here we have an induction function. Then Cosson proved that these two categories are equivalent via this Wien-Take function and this induction function. As a result, the classification of simple objects in objects in EG5 mode, just irreducible reputations of the center, yields classification of simple objects in n theta. However, for Lie superalgebra, this Cosson theorem no longer holds. In fact, there is an equivalence from n theta to the finite-dimensional module category over certain principal finite W superalgebra. So in the case of in the super case. So let's denote these simple objects by YG, Y sub G, depending on chi theta. Since we have already seen the simple, since ZG are polynomial algebra, so central characters give rise to simple ZG modules. Before we explain the super analog of Cosson's theorem, we now move on to the complicated classification of simple Wien-Take modules. Now suppose that G is arbitrary quasi-reductive Lie superalgebra with neo character. We may block neo and Levy subalgebra of the even part, such as we choose a maximal Levy subalgebra of this even part, such as the retreation of theta to the intersection of neo-radical and this Levy is non-singular. So this allows us to define Wien-Take Cosson type simple Wien-Take module here. And furthermore, we assume that this algebra is also a Levi subalgebra of G inside a parabolic subalgebra P theta. So we can form a parabolic induction. So this is this is McDowell's definition of standard Witten modules, but we can just follow the formulation of McDowell to define standard Witten modules for Lie superalgebra. So here, chi lambda denotes a central character associated to a weight lambda. For example, if theta is 0, we have just seen the Witten block N0 consists of all G modules, finite G modules with high composition factors. In this case, since theta is 0, so it is impossible to find non-trivial neo-radical such that these conditions is satisfied. So that means theta is non-singular. So in this case, we have so in this case, the Levi subalgebra is just a Cartan subalgebra, and the parabolic subalgebra P theta is just the Borel subalgebra, and standard Witten module reduced to the ordinary Verma module with high lambda. Here lambda is, here we induce from a cosine type simple Witten module, and the lambda is used to construct a central character. And it turns out that simple Witten modules in N theta can be classified in terms of tops of these simple Witten modules. So let's keep the same assumption that G is quasi-reductive and theta is arbitrary character such that theta is Levi subalgebra with G. Then in this case, each lambda theta, the standard Witten module has a simple top denoted by L lambda theta. Furthermore, the set of L lambda theta is a complete list of all simple operators in the Witten block N theta. And standard Witten module and the layer tops L lambda theta are parameterized by wire group, by the orbitals under the wire group action. Here, wire group is a wire group of the Levi subalgebra L theta. And furthermore, each standard Witten module has finite length. So, for example, if we consider the case when theta is 0, then we have Verma module. Then tops of Verma modules classify simple up. We've just seen top of the Verma module classify simple operators in N0. And according to certain item, each standard Witten module has finite length. We can talk about composition multiplicity of these standard Witten modules. For GLN OSP, the multiplicities are given by bounded and Cauchy-Lewis theory due to Chen Lan 1 and Bao and 1. And in general, we can always define standard Witten modules, but if we drop the condition that L theta is Levi subalgebra of G, then we reduce the problem to that of multiplicity problem to that of sorry, the classification problem to that of principal finite double algebra, and in this case, multiplicity problem can always reduce to that of Riemann modules. Here, I would like to mention some recent programs on the study Witten modules for least superalgebras. There is a variation of category, Witten variation of Witten category O, which has a straightwise structure rather than high-thread category structure given by for type 1, myself and Chen and Mathematicians, and beyond type 1, we have some similar results, and we have some categorification of some symmetrized Fourier space. And we take vectors in the principal case, realize finite-dimensional representations of principal finite double algebra. And there is a remarkable superduality for Witten modules and finite double algebras proved by Chen and Wang. And more recently, we explored irreducible representations of finite supersymmetry double algebras, which I will explain in the next part of this talk. So this is the first part regarding Witten modules over least superalgebra. So now let's move on to double algebras. Here the table summarizes the landscape of double algebras. On the left, we have classical side. On the right, we have quantum side. For finite case, the foundational work starts with cosine in 78 and was greatly studied by Primate for the general case. Below that, we have alpha W algebras, which are important in the study of vertex algebra, and with key contributions by many people. So quantum double algebras arise as quantization of classical ones. They can be obtained via Hamiltonian reduction. So in this talk, we focus on the finite case. Since the construction of supersymmetry finite double algebra is similar to the classical one, so let's review the construction of finite double algebra via Hamiltonian reduction. So to define the classical finite double algebra, we need the following ingredients. We fix a finite dimensional reductive Lie algebra with a nilpotent element E. And we fix a non-degenerate invariant symmetric binomial form of G. By Jacobson-Morov theorem, we can embed this nilpotent element E into a SL2 triple for this reductive algebra G. And a joint action induces so-called decaying gradient of this reductive Lie algebra G. So now we have a gradient on G, and we fix a simplified form defined involving the invariant form and the nilpotent element E on the subspace G of -1. And we, by choosing a Lagrangian subspace with respect to this spin-T form, we can construct a nilpotent subalgebra M. So it is the direct sum of this Lagrangian subspace and the direct sum of this G of I ranging from -2, -3. This together with character theta. Now theta is defined as restriction of the form we have just seen here. Is indeed a character of this subalgebra M. Will be important in our reduction process. Classically, if we take the symmetric algebra of G, which is a Poisson algebra, and then we perform the reduction, essentially taking invariance of this quotient of symmetric algebra SG under the adjoint of M. Then we obtain the definition of classical finite W algebra. And this is isomorphic to the Poisson algebra on the slowly slice. So the polynomial algebra of the slowly slice. Since UG is a natural quantization of this Poisson algebra SG, so the following is a natural way to define quantum version of finite W algebra, UGE. So here we replace Poisson algebra SG by UG, and we perform the reduction. So quantum finite W algebra is defined as invariance of this quotient under adjoint of M. This algebra inherits inherits multiplication from UG. So the multiplication is very natural. So this is a definition of quantum, the finite W algebra UGE. This construction has a generalization via the so-called good gradient for a nilpotent element. For example, now we assume G to be reductive. For example, if E is 0, so E is 0, then no reduction happens. So we get UG. Because no reduction, so UGE is UG. It's just a universal enveloping algebra. Another extreme case, when E is principal, so that means theta is non-singular, then UGE collapses to the center of G. In this case, M is a radical. So finite double algebra provides rich algebras, examples of algebra interpolating between UG and ZG. Such a construction extends naturally to the superalgebra. The theory of finite double algebras has been extensively studied by many people, start from Constant and Leach and Primate, Gang Ginsberg, Bounden, Goodwin, Kashif, Losef, and other people, and was extended to finite W superalgebra for basic and type Q. The superalgebra, for example, by Bounden, Brown, Goodwin, Zhao, and Politava, Sukhanova, and Suzanne, and Suxiao, and Peng, and myself, Xuan Chen, and others. For type P, we, in my recent work with Xuan Chen, we have also extended to type P Lie superalgebra, and we formulated the finite W algebra. There is an important connection between UG and UG modules, originally proved by Skhiriabin, known as Skhiriabin equivalence. So let's review Skhiriabin equivalence here. We first assume G to be reductive Lie algebra with nilpotent element E, and we shift the M by theta. Here we recall that theta is, we first recall M is the direct sum of Lagrangian and some gradient subspace, and we use invariant form and the nilpotent element to contract character theta. Here, and theta denotes shift M by theta. And we consider the category of generalized Witten modules, namely G modules on which elements of M theta acts locally nilpotently. Then now we can state the Scriabin equivalence, which is a generalization of cosines equivalence. So Scriabin equivalence states that the Witten function, so this is just a function of taking Witten vector, defines equivalence between these two categories, generalized Witten module category and the category of modules over finite W algebra. This equivalence has been generalized to basic classical and strange. For basic classical, generalized by and Qn by Zhao and Su Xiao, and for Pn, in my work joined with Chen. And in particular, Scriabin equivalence for Lie superalgebra, for both Lie algebra and Lie superalgebra descends to equivalence of categories N theta and finite dimensional module category of the corresponding finite W algebra in the case when E is principal. In a non-principal case, which means so in a non-principal case, there's a remarkable connection between N theta and category O of modules over finite W algebras. So which descends to equivalence of category of N theta and the finite length subjects in the category O of UGE modules. This category was originally formulated by Bond and Goodwin Kashif. And this approach, this was first proved by Losef, and for reductive Lie algebra was extended to basic classical Lie superalgebra. And for type Q, in my recent work with Chen, we have extended this equivalence to type Q Lie superalgebra. So now, in the final part, I will present our results on finite supersymmetry W algebras. We discuss some connections with the Witten generalized Witten categories and the Witten category in the sense of McDowell and Minsky circuit. So the setup is we continue to assume that G is a basic classical Lie algebra, and we fix a non-degenerated supersymmetry invariant form. Then we form the Takif superalgebra with odd generated set. So as an underlying space, it is a copy. It is a direct sum of two copies of G, and the former is isomorphic as a as a Lie superalgebra. The later is Lie superalgebra And such a superalgebra is called Takeyuki superalgebra. Then we can form the central extension of it, denoted by G2. So the central extension is given by a central element C spanned by Z, with the following bracket. In the commutative formula, we have Takeyuki bracket in the first term, and we have certain central term involving the invariant form and the partial derivative partial theta. So this central extension of Takeyuki superalgebra. So we start from basic classical Lie superalgebra, then we have Takeyuki superalgebra, then we do the central extension. The construction of finite W supersymmetry finite W superalgebra is similar to classical one, but with key difference that we use OSP embedding rather than SL2 embedding. So we fix OSP12 embedding, which contains E, such that EF denote EFH from the SL2 triple, and capital E and capital F and H from SL2 triple, and the lowercase EF, E and F are the elements. And then similarly, we use a joint action to induce the grading of this central extension of Takeyuki superalgebra. So now we have a grading. And then we define the a similar nilpotent subalgebra. So it's the Doric sum of G tutor of I degree I ranging from -1. And we define a character as follows. Use invariant binary form of G and the partial derivative and this E. And the finite, then the finite supersymmetry W algebra at level C. Here C is complex number, is defined as a invariance of this quotients under the adjoint action of N. So this is also a quantum Hamiltonian reduction definition of finite supersymmetry W algebra, finite supersymmetry W algebra, where C means we quotient out the central element Z minus C. So one of our motivations is to study irreducible reputations of supersymmetry W algebra. So N equals to 1 supersymmetry vertex algebra is vertex algebra equipped with odd derivation D, such as D squared. Since now it is vertex algebra. So we have a translation operator, such as D squared is a translation operator of it. Similarly, we have a supersymmetry version of alpha W algebra, which is denoted by W upper K sub N equals to 1 of GE. So it depends on GE and K. Is supersymmetry vertex algebra defined by the cohomology of supersymmetry BRST complex of this form. So this is a tensor product of supersymmetry version of alpha vertex algebra, and the later vertex algebra is just the Feynman vertex algebra, but with a supersymmetry structure. So which means we have other derivation. So for in the study of vertex algebra, Zhu's correspondence explain a correspondence between positive energy simple modules of vertex algebra and simple modules of Zoo algebra. In this supersymmetry picture, we have indeed we have there are isomorphism between Zoo algebra and our finite supersymmetry W algebra. Let's explain the assumption. Suppose that we assume non-critical level condition, which means K, the complex number K, the label K is chosen to be such that K plus H check is non-zero, where H check is a dual coexistent number. Then under this condition, there's an isomorphism between supersymmetry, the supersymmetry of W algebra and the Zoo algebra proved by Genra, Song, and Su for principal case and Lin Xiao, Song, Su for in general. So according to Zoo correspondence, simple module can be classified. Positive energies module for the SUSY finite W algebra can be classified by simple modules of finite SUSY W algebra. Our result is that is the following equivalence. We continue to assume the non-critical condition, label condition, and we choose nilpotent subalgebra of G such that, there's tilde missing here, such that, such that M is a tensor part of M is. So we just take the intersection of M and G. Then we can contract, so this is a nilpotent subalgebra. Then we can contract a character as follows. Character of the even part of this nilpotent subalgebra. Then the result is that there is an equivalence of category of generalized Wien-Taken modules and the module category of finite SUSY W algebra, which is a composition of Wien-Taken function, of taking Wien-Taken vector and tensoring with a certain Fock space.